Okay, let's take a look at section 2.4 of your book. It covers a topic that I'm sure some of us, perhaps many of us, have heard of before, something called acceleration. Even if you've heard of it, it can still be conceptually a challenging quantity to fully understand and apply in the classroom. We'll see that it lays a foundation for most all of Newtonian mechanics, so we really need to understand this concept pretty well. Now, students will often confuse various aspects of acceleration with velocity. They are not the same thing, though they are related. Now, a couple years back, I had a student, an exchange student, happened to be a pretty good artist. On her way out the door at the end of the year, she gave me a nice poster. I'll show that to you in a moment here. Students more recently have said, Ms. Treisinger, we really like your video lectures. They're very inspiring. Thank you very much. But we'd love to have a webcam of you so we can see your face as you're presenting. We'd like to know what you look like. They informed me that that would be a reveal, that if I were to show my face while I'm presenting. So here we go, a reveal for you. Here I am on my hoverboard carrying my my little air cannon, wearing safety glasses, safety first, got my scraggly beard going, and sure enough, you don't just go faster, you accelerate. And I'm saying take physics, so a little advertisement there. Thank you, Nguyen, from 2018. Really like your poster. Show this every year, and I hope you're doing well. So students will often confuse them. Let's see if we can sort of make sense of how they're different. Whereas velocity is the rate of change of position, acceleration is the rate of change of velocity. Now, to illustrate what it means to be a rate of change of velocity, let's take a look at this example. This is not quite the car that I bought when I was a young lad like you, 15, 16 years old. My first car was a 1976 Dodge Omni, and I bought it from my neighbor, and loved that car. Wasn't the highest performance car, and I'll explain that here in a minute. The neighbor, he's like, hey, you should buy this car. It can go 0 to 60. And I was so naive. I'm like, yeah, I got to have that car. So 0 to 60, no way. And then I forgot to ask the question, well, how long does that take? Because you recognize 0 to 60 is simply a change of velocity. Well, acceleration is the rate of change of velocity. So it's not just 0 to 60 that's important. It's how long it takes. It turns out after I paid the cash, I'm driving the car down the road, and I timed it. It took about 20 seconds for me to go from 0 to 60, so certainly not a high-performance vehicle. I learned my lesson nonetheless. I still love that car. Be careful on the road, please. Average acceleration, let's go ahead and define it as an equation based on this definition up here. It's just simply a ratio of change in velocity per time elapsed. And with that, we can start to look at what its units may be. I'm going to start with considering my car, or at least some sort of replica of that car. Delta V compared to delta T. Well, let's see. Delta V, I went from 0 to 60, so 60 miles per hour. I'm not going to put -0 there. I started from rest. And the time interval, it took me about 20 seconds to do that. And so 60 over 20 is pretty easy. Well, acceleration is not just 3. There are some units there. Those units help us understand what we mean by a rate of a rate. 3 miles per hour per second. You can see we have some mixed units here. We have units of velocity, and we have units of time. So when we look at how we quantify acceleration, you're going to see some confusing units. It may be the first time that you actually have used these units in a scientific setting. You may have seen them before, but we will see these units a lot in this class. Now, these are not SI units, but they are understandable. My car, 0 to 60 in 20 seconds. If it continued accelerating at this rate, if it were constant, then every second my speedometer would go up by 3 miles per hour. So you can think of acceleration as the rate at which the speedometer needle, if you have an analog device like that, the rate at which it's sort of moving along the dial. The faster it moves along that dial, the higher the rate of acceleration. This is actually very low. Some of you probably have vehicles. I would guess that all of you have vehicles that would outperform my old 76 Dodge Omni. Let's look at the SI units for this. The SI unit for velocity is meters per second, and the SI unit for time is a second. We often abbreviate that as meters per second squared. This is the way you'll see it written in your textbook. It's the way you'll see it written in various numerical solutions or solutions to your homework problems and so forth. It is not as intuitive as this here. I like the meter per second, and oftentimes, especially in the beginning stages of the class, I will say meters per second per second. Now you can change the velocity of something by changing three things. In your car, you have three accelerators. You have the gas pedal, you have the brake pedal, and you have the steering wheel. As these three pictures show, you can speed up, you can slow down, and you can turn. So let's go ahead and summarize those. You can change the velocity by changing its speed. You can change the velocity by changing its direction. Of course, the third one, the one that you may not realize, so you can do both at the same time. Perhaps you're on an on-ramp or an off-ramp where you're both speeding up and turning at the same time. Certainly can do that. Now, an interesting side note, I want to continue on trying to build a conceptual understanding of acceleration. You may not have ever thought of this, but certainly you can relate to this. You cannot sense motion. You cannot sense velocity. You don't even know if you're moving. Take yourself in a vehicle going 60 miles per hour down the road. Perhaps you're in the passenger seat. You could read a book. You could fall asleep. You could not even know that you're moving if you don't look and see the trees moving from the side of the road, or if there's no bumps on the road, you don't even know you're moving. Now, you can sense acceleration. You can sense changes to your motion. So if the driver of that car steps on the gas, you're going to feel it. If they hit the brakes, you're going to feel it. If they turn, you're going to feel it. So you can only sense changes in motion. We don't have the ability to sense motion. All right, let's continue on. Now, this video is going to be quite lengthy because of the examples that we're going to look at. The examples are quite a bit more elaborate than what your book goes through, and the reason for that is I need to start introducing this concept called multiple representations. The AP test is going to require that you know multiple ways of presenting motion with these various tools, or interpreting motion with various tools, and we want to develop that now. So let's see. Average acceleration, example 2.4, a car accelerates along a straight road from rest to 90 kilometers per hour in 5 seconds. What is the magnitude of its average acceleration? Well, that's not too hard to do with an equation. We've already done that before with my other car there. So let's go ahead and try that here. With an equation, average acceleration, change of velocity per unit time. Doesn't really matter what units we use, so I'm going to stick with these. 90 kilometers per hour minus 0 all over 5 seconds. It just turns out to be 18 kilometers per hour per second. Since I don't have the same time unit there, I'm not going to use any squared units, just kilometers per hour per second, and that's fine. Now, if you want to write that in SI units, which might be preferred, not necessary, but you might prefer to do that, 90 kilometers per hour, well, if you think about it, there's 1,000 meters in a kilometer and 3,600 seconds in an hour, so effectively just divide that 90 by 3.6, and you'd get that is 25 meters per second. So a little bit of a double conversion there. 25 meters per second change within 5 seconds means that is an acceleration of 5 meters per second squared. I'm going to drop my significant figures there for a second. Both of these are acceptable ways of presenting that. Now, let's take a look at a diagrammatic way of presenting this. Diagrammatic means you're going to create or interpret a diagram. We often call these dot diagrams or strobe diagrams. Imagine taking a picture of this car at repeated time intervals that are spaced equally apart. You would see that the position of the car is changing with time. If we were to represent the spacing of those dots, allow that spacing to sort of indicate how fast they are moving between those time intervals, we can then use a dot diagram to represent accelerated motion. Now, this is showing the dot spacing increasing as we go to the right. How do we know that it's going to the right? We typically put little arrows on here that represent the velocity vectors. So you can see that this is getting bigger. The velocity is getting bigger as time goes on. Now, the next thing that we would show on a diagram, or a strobe diagram for this, is a dot diagram showing the acceleration vectors at these various points. Now, the acceleration is constant throughout. This first unit is going to deal with just constant acceleration until we get into some calculus ideas later on. And so we're going to assume that the acceleration is a constant value of 5 meters per second squared. So when I go to draw that, I'm going to be showing these arrows to be the same size throughout. And I might label one of those with an acceleration vector. Now, what's really important here is to recognize that both these vector quantities, remember, vectors are things that have direction. We'll study that in a lot more detail in chapter 3 when we start considering 2D and 3D motion. For now, we just consider motion in 1D. It's not too bad. Velocity and acceleration in the same direction causes objects to speed up. You want to think of acceleration as the rate at which velocity changes. If it's in the same direction as moving, then you would see that the next point in time, it's actually become longer because we've increased it by that amount multiplied by a time interval. So you can see that the direction of the acceleration in relation to the velocity becomes important. That determines what happens to that object. Now, last thing we're going to look at is a graphical representation of this. For those of you that are in calculus or have been through calculus, you've done a lot of graphical work already, so this should be fairly quick for you. Maybe a little bit of a review. If you're new to calculus, maybe this is brand new, but you'll see that we'll get pretty good at this with time. Let's go ahead and take a look at the acceleration first. It is positive and constant. That's easily drawn on this graph. The velocity, starting from rest, and it's increasing uniformly. I'm going to make these things a different color so it's easier to distinguish them from the axis and from the graph. So the velocity starts from rest and accelerates, and the velocity increases uniformly. Let's talk a little bit about slopes. Acceleration is the rate at which velocity changes. Well, rates can be found as slopes of lines on graphs. So if I were to take that and take a look at the slope of a velocity time graph provides the acceleration graph. And finally, the position versus time graph. Throw some axes on here for a minute. If we consider that this is the origin, if that's where we're going to start our measurements from, then it is starting at the zero position. As time goes on, you can see that the dots are getting consecutively further apart as time progresses. Certainly, you can see that that would yield some sort of quadratic relationship. We get a nice little parabolic curve there. Let's do a quick little connection. We said that slope of position time graph was equal to velocity. We see the slope is constantly changing, but we did talk nonetheless about slopes of lines tangent to those curves, and certainly you can see shallow slope, medium slope, steep slope corresponding to those velocities. Okay, so there we go. First example, let's move on. Here we have example 2.6, a car slowing down. An automobile is moving to the right along a straight highway, which we choose to be the positive x-axis. The driver puts on the brakes with the initial velocity. When they hit the brakes, it's 15 meters per second. It takes 5 seconds to slow to 5 meters per second. What's the car's average acceleration? Again, let's start with an equation representation. A equal to the rate of change in velocity. I went from, let's see, the final velocity is 5 meters per second, the initial velocity 15, and then the time interval 5 seconds. So we see that we have a negative delta V. Do that math, it's negative 2 meters per second squared. Probably supposed to have another digit in there, negative 2.0 meters per second squared. Now what's important here is, again, the direction of that acceleration is leftward on my diagram. And I know that because it's in the opposite direction of the object's motion. Okay, and so we would say that it is moving to the right, but accelerating towards the left. Now let's take a look at a diagram of that. Let's use black for this. Object is moving towards the right, but now the beginning of its motion is very fast, and so the dots are going to be further apart in the beginning. And then these arrows here would become smaller to indicate that it is slowing its rate of motion. Now from an acceleration standpoint, again, we sort of line up the dots above and below the other ones. Ideally, we'd like to be able to have those right on top of each other, but it gets a little too complicated. I see I'm sort of trending upward there. Don't worry about that. The acceleration is this way, and again, it is constant. So when I go to draw these, I would attempt to draw them all the same size. Okay, and we would label one of these as A. So there we go, a dot diagram. Really help understand this if we can draw these graphs. So let's go ahead and start with acceleration again. I know the acceleration is negative according to my chosen coordinate system, so I'm going to go ahead and draw that first. Looks like that. The velocity, see, the velocity is positive, so I'm going to go ahead and keep that up in quadrant 1 on a standard XY plane. And but we start with a rather high velocity and we end with a lower velocity. So because this is happening uniformly, we would expect straight lines here. Slope connection. Negative slope shows as a negative acceleration down there. And finally, our position time graph. Let's see, we're starting. Let's go ahead and say that this is my origin again. And so we're moving in the positive direction. And so we're starting here. And let's see, we're starting out pretty fast. And we're ending at a fairly slow rate. And so the connection in between looks something like this. And again, this is just a qualitative sketch. It's important to get those relationships down and understanding what accelerated motion looks like, both on an xt graph, a vt graph, and an at graph. Okay, so there we go. And let's see, just that connection again, slopes of a line, tangent. Make sure I did that right. I do this myself quite a bit just to make sure. Steep slope, shallower slope, looks good. I like it. Another one done. Let's take a look at this last one. There is a difference between negative acceleration and deceleration. Okay, so oftentimes people will say if something has a negative acceleration, that means it's slowing down. That's not the case. There is a difference. Negative acceleration is acceleration in the negative direction as we define it. So it really depends on our choice of a coordinate system. And again, remember, you are free to choose which way you want to call your positive and negative axes. You need to be consistent once you make that choice, but you are free to choose. Deceleration occurs when the acceleration is opposite in direction to the velocity. So you need to be careful there, that not associating negative acceleration with slowing down, not associating positive acceleration with speeding up. Okay, it depends on how those two vector quantities are aligned. That's another one of those tricky areas that students sometimes grapple with. Take a look at a way of illustrating that with this example. Here we have V1 and V2, so the car is moving towards the left. You can see it's starting out with a high rate of speed in the beginning and a slower rate at the end. Which way is this car accelerating? Is it accelerating towards the right or to the left? It's slowing down, so certainly it's changing its state of motion. What's the direction of that? Is the car's acceleration positive or negative? I'm trying to answer those two questions before I show you that. Okay, so here we go. Which way is the car accelerating? It's actually accelerating towards the right. And I know that because the car is slowing. Slowing velocity means acceleration has to be in the opposite direction. So its acceleration is rightward. According to our coordinate system, we've defined leftward as negative. So therefore, the car's acceleration is positive. Positive acceleration here means slowing down. Let's take a look at a diagram. I'm going to move this up here. A bit easier to draw. Now, this becomes pretty important. Usually we like to read left to right. Well, here we have motion towards the left. So it's starting out with a high rate of speed towards the left, and as time goes on, it's moving more slowly. So putting these arrows here certainly helps indicate which way it's moving. Okay, so these are velocity arrows. Acceleration arrows would be everywhere constant, but positive. This gets a little bit tedious after a while to draw these, but nonetheless, it is important for you to understand how to draw those and how to interpret those. Okay, so that'd be a diagram. And finally, the graphical way of representing this. If you haven't tried so already, pause this and see if you can draw these graphs yourself. I'm going to go ahead and draw these axes here. Okay, now, hopefully you've had a chance to pause it and try these. The acceleration, again, we know it's positive. We don't know the actual value, but it is accelerating towards the right in the direction that we call positive. The velocity starts out very large and negative, ends up very small and negative. So we're going to say that it's starting out like this and going here, and it's doing so uniformly. Again, slope connection. Negative velocity, but you notice a positive rate of change in that velocity. That slope is still shown here as a positive value. And finally, the x as a function of time graph. Let's go ahead and define this as my origin. So I'm starting here, moving in the negative direction. I'm going to fix my graph right now. I can see that I'm going to want to move that up here. So I'm starting at this point. Because I'm moving in the negative direction. I'm going to be in quadrant, let's see, quadrant 4 of your standard XY plane. Starting with a high rate of speed, negative velocity in the beginning, and ending with a little bit, with much less speed. And sure enough, it'll look something like this here. Slopes of line tangent. Seems to make sense. Very steep but negative, shallow but negative. And sure enough, I'm in that negative area for that graph. So there we go. Now the rest of this video is just for my AP Physics course. It has to deal with a little bit of calculus. So if you are in general physics and watching this, feel free to stop the video. For those of you that are in calculus, I'm going to go through a little bit of theory on how we get to instantaneous acceleration, and also look at the quantitative example. Let's go ahead and continue. So the instantaneous acceleration is the average acceleration in the limit as the time interval, again, becomes infinitesimally short. This is very much like how we got instantaneous velocity from average velocity, very similar. If I had a graph of velocity versus time, I could certainly construct a line tangent to a curve at any point, measure the slope of that, and get an instantaneous value graphically. However, if we're going to use calculus, we can use that limiting technique of letting delta t approach 0, and then take the ratio of delta v to delta t. We'd see that that approaches the instantaneous acceleration. Now again, in your calculus class, you do a lot of theory that allows you to eventually skip over this, right? So be sure not to skip that. Calculus theory is important for you to understand, particularly if you're taking the AP Calculus test. You need to understand this process pretty well. For us, we're going to go ahead and just take the instantaneous acceleration as the rate at which velocity changes with time through that derivative process. Okay, so again, you'll see the connections between your calculus and your physics course over the course of this year, and certainly that will help you. Now, let's take a look at this last example. Here we have example 2.7 from your book. I may have modified it slightly. Well, it looks like I have two examples here. A particle is moving in a straight line, so its position is given by the relation x is equal to 2.1 meters per second squared t squared plus 2.80 meters. Calculate its average acceleration during the time interval from 3 to 5 seconds, and its instantaneous acceleration as a function of time. Now, truth be told, generally in your calculus class, you are given these kinds of expressions where they say x varies with time in some way. In reality, in physics, you're going to see that we rarely see equations that are written with just constants out in front of t squareds and so forth. We usually use the kinematic equations, the things that we talk about, the equations of uniform acceleration that we will use for the throughout the course of the entire semester. So this is much more of a mathematical way of presenting this kind of motion. You'll see more physics-based things as we progress through the course. So nonetheless, let's take a look at how we might find its average acceleration during the time interval from 3 to 5 seconds. Now to do that, the average acceleration, let's go back to that definition, delta v over delta t. Well, I can do that by finding the velocity so the instantaneous velocity at 5 seconds. I'll write that using that notation, and subtract from that the velocity at 3 seconds. And then divide that by the time interval from 3 to 5 seconds. That'd be 2 seconds. Okay, so now the question becomes, how do I find the velocity at 5 and 3 seconds? Well, I do that by using my position function, and I do that by using some calculus. We know that the instantaneous velocity can be found from the position function by taking the derivative of that function with respect to time. And so when I take the derivative, you'll see again that the derivatives are usually pretty simple in my class. 2 times 2.1 is 4.2. Let's keep those units there, meters per second squared, times t. And then let's see, I take the derivative of 2.8. It is not time variable, so therefore when I take the derivative of that with respect to time, it becomes 0. And so now I can go ahead and calculate v at 5 by simply plugging in 5 for that. Let's see, 4.2 times 5, looks like that's about 21 meters per second, if I did that correctly. And the velocity at 3 seconds, and I get, let's see, 12.6 meters per second. So there, I can go ahead and now determine the average acceleration during that time interval by taking, let's see, 21 meters per second minus the 12.6 meters per second, and that occurs over 2 seconds. And for that, we get about 4.2 meters per second squared. So there we go, the average acceleration during that time interval. Letter B, what is the instantaneous acceleration as a function of time? Okay, so letter B, if I'm going to find instantaneous acceleration, I'm going to take the derivative of the velocity function with respect to time, and sure enough, that derivative is fairly simple as well. You just get 4.2 meters per second squared, and that is a constant value of acceleration. Oh, looks like that makes sense. Average acceleration is the constant value since it's uniform. Okay, let's go ahead and draw these graphs. I want you to take a moment, if you haven't done so already, to try to draw these graphs on your own. We've done quite a bit of study so far, just in this lesson alone. So see if you can do it. Okay, here we go. Position versus time graph. Should look something like this. Notice I'm starting a little bit ahead of my origin, 2.8, and got a nice little quadratic relationship there. Velocity is increasing, and we'll see that that looks like this. Increasing uniformly, I should say, and the acceleration calculated 4.2 meters per second squared. I like it. Last one, conceptual example. This figure shows the velocity as a function of time for two cars accelerating from 0 to 100 kilometers per hour in a time of 10 seconds. Compare the average acceleration over the entire time. Find the instantaneous acceleration at 1 second and 8 seconds. And letter C, the total distance traveled for the two cars over the entire time. Let's take a look at letter A. Compare the average acceleration over the entire time. Well, we see they have the same change in velocity. The average, again, would just be found by taking the slope of that line. It doesn't matter how they got through that change in velocity. It occurred at the same rate, so they both have the same average acceleration. Letter B, their instantaneous acceleration at 1 second. Well, 1 second, I'm going to look at slopes of lines tangent to these curves. And 1 second right around here versus right around here. So it looks like car A is accelerating at a higher rate at 1 second. Now at 8 seconds, that's over here, we can see that now it looks like car B has a little bit steeper line there, and so it looks like car B is accelerating at a greater rate at that point in time. So again, I guess it depends on where we look within that 10-second window. I'm not going to write that in here. Now, letter C, the total distance traveled by the two cars over that entire interval. Now, there are other ways to do this that involve higher level calculus than what I'm going to show you right here, but we can see that during all points in time, except for right at the very beginning and right at the very end. Car A was traveling at a higher rate of speed than car B, so since it was always traveling faster during that time interval, except at the endpoints, it had to have covered a greater overall distance or displacement during that time interval. And so the other way to look at that is through an integration technique, and it has to do with area underneath the curve. And it's probably quite a bit of a stretch if you're going through calculus right now to even talk about integration. It seems like it's usually a second semester topic down there in the hallway. So I'm going to save that discussion, but certainly areas underneath curves become pretty important physical, represent some pretty important physical quantities. We'll get to that a little bit later. So there we go. That completes the lesson on section 2.4 for both general physics and AP physics. Hope you enjoyed it.